And the first thing to think about really is about what the role of security is within an embedded system, not just a Linux system. It's about making sure that the intended operation of that system can't be misused or subverted for some nefarious purpose. So when you're designing a system, you of course design it to work correctly. You know, it needs to do what it needs to do. But when you're thinking about the security of that system, we need to take things onto another level and think about how or what possibilities there are that that system could be misused. And the device could be misused to do other things. I mean, devices typically, as shown here, don't exist in isolation. They're interacting with other devices, they're interacting with users, with cloud services, for example. And if somebody's able to misuse this device, then that could have obviously much wider implications, as well as, of course, the implications for things like personal data and so on the device itself. So security protects against device misuse, and misuse might be possible because of flawed design or weaknesses in software. And so a lot of the things we're going to speak about today are about defeating or at least mitigating against those things. So one way to think about how your system could be secured is to think about how it could be attacked. And we can do that using what's called an attack model. This is a simple example here where we have the system itself in terms of the hardware, the software. There are potentially weaknesses and known vulnerabilities in that hardware and software. We need to be aware of those. We need to think about what the people or bodies or organizations or whoever it is that's going to create a threat. These are sometimes called threat actors. So we need to have some intelligence. Who might try and attack our system? And when they do attack the system, they're going to be looking for an entry point, an attack vector, so-called. And the sort of set of attack vectors is sometimes referred to as the attack surface. And so we need to think about what countermeasures and controls can be put in place to limit that surface. What exploits are required? Another part of this is to think about what assets are potentially at risk. You know, what is the data that could be exposed? Is it, financial information? Is it personal data? And we need to carry out a risk analysis. We need to look at the potential impact of any attack and the cost of actually fixing that attack, the likelihood of that attack being successful. And so this is all part of a process often called threat modeling, which is about trying to understand your system and the potential for attacks on that system. And that should be done very, very early on in the design process. So there are lots of industry standards and also self-assessment frameworks as well. We've picked out a couple, as you can see here, one from ETSI, which is quite well known, another one here which is a whole series of safety and cyber security requirements. I'm not going to get into the details of different standards. It ends up with a lot of numbers being read out. We're going to focus on the ETSI requirements as an example of the sort of standard that can be applied to an embedded system. This information on the bottom right hand side here is from an industry survey by ARM, and it's quite interesting to see how organizations evaluate their security. And what you can see, that I don't know if you can read the text there, we've got internal evaluation, third-party consultant, and external lab testing. And you can see by the size of the numbers there that most organizations carry out several different ways of assessing their security compliance. They may do an internal evaluation, but they will also look for external lab testing as well, for example. So the ETSI EN 303-645 security standard, Cyber Security for Consumer Internet of Things Baseline Requirements, which was published a couple of years ago, defines 13 provisions. Now it is for consumer IoT, but I think we can apply these across any sort of embedded system, any embedded Linux system that exists. So I'll just go through these very, very quickly. No universal default passwords, keep software updated, communicate securely, ensure software integrity, make systems resilient to outages like power outages, for example, make it easy for users to delete user data, validate input data, implement a means to manage reports of vulnerabilities, securely store sensitive security parameters like passwords, for example, minimize the attack surface, make sure personal data is secure, examine system telemetry data for security anomalies, and make installation and maintenance of the device easy. So these are all, pretty straightforward, low-level requirements. You could say it's common sense, but of course there are numerous cases where devices have been successfully attacked, and you can argue that common sense hasn't been applied in many cases. So we're not going to cover all of these in this pretty short presentation. So I've picked out just a few of these that we can look at in terms of, as I say, the features of a typical embedded Linux system. So as we go through the presentation, we'll be looking at particular features, tools, etc., and then looking at which of these requirements, these provisions, they can be used to try and satisfy. So the first thing to think about is how vulnerabilities in products are actually exposed publicly. The right thing to do, of course, if there's a problem with the device, is to let people know. And there's a project called the CVE project, the Common Vulnerabilities and Exposures project, which is used by vendors, software distributors, software projects to publicly disclose vulnerabilities in their products, hardware or software. And there's a sort of standard format. Everyone is given a unique number with a date and an identifier, a description, information about how the weakness can be triggered, and the aim, of course, is that people who are using the particular piece of software in the product can monitor these and can react accordingly. Another project that we'll look at a bit more detail is the Common Weakness Enumeration Project, CWE, which is about classifying weaknesses in software in particular, but also hardware, by the sort of type of the error, and we'll look at those in a little while. So one of the ETSI requirements was to implement a means to manage reports of vulnerabilities, and part of that is making use of the CVE project, announcing publicly, we have detected a weakness in our product, but we are going to fix it, update your firmware to version XYZ, and the problem is resolved.
Doulos is a training company providing expertise and specialist training worldwide in all of the areas you can see on screen, from SoC design and verification, FPGA and hardware design, to embedded software and Python and deep learning. You can watch the rest of Simon's webinar, Getting Started with Embedded Linux Security, whenever you want, by heading over to our website www.doulos.com/OD and registering for free. For more free tips and tutorials, visit the know-how area of our website, and don't forget to subscribe to our YouTube channel. Thanks for watching.